it was more of an online lecture, I believe. So I also believe that most of you might have seen that. So lecture 17 was about Newton rational load flow, and I thought instead of going into a new topic, I will first review what I have done in the last class because there has been a break of more than a week. So let's do a quick review of the previous class, and then we will continue with the other topic. So that's why at the screen. So first I want to do review of Newton rational load flow and plus fast decoupled load flow. I would like to, if time permits, I would like to cover or start the fast decoupled load flow problem also. So there are, first I would like you to have a look at this link that is there on your screen, sites.google.com. So let me just share the screen. I'll show you what that link is. So anybody can go to that link and open that. So I'll be showing you that link, notes also. And you had also seen that most of the time we are trying to do some MATLAB coding. So the MATLAB codes also I have attached. You can download that for that particular lecture. And then this red color symbol is actually the lecture notes in PDF. So this also you can download. And you notice that the video, once I receive the video for all the other links, I'll put up that video link also for the other lectures. But whichever lectures I have the access to the video, I have just added that video link also. So I hope and I believe that you might have seen this these videos. Those who could not attend the lectures, please look at the video. Please practice these videos, and before coming to the class, try to revise your previous lecture because power system subject is such that there should be continuity. And if there is continuity, only then you will be able to understand the next class. So especially today's class, it's if you don't know Newton rational load flow thoroughly, then it is difficult to understand the fast decoupled load flow because fast decoupled load flow is something that we build on top of the Newton rational load flow. Okay, so with that note, let's just start. So my question is that since this is an online class and then there are several students attending this in live, you just ask yourself, if I give you a two-bus system or a three-bus system with three unknowns, can you solve the Newton rational load flow problem? So what are the equations that you need write? What are the steps that are involved? Whether you can use a calculator or you can use a computer, can you solve it yourself without referring to the books? Of course, you can refer the books, but then first question is you understand that procedure or not. So that is the first thing you should ask yourself. So, and I believe that most of the time, since this is since there has been a break for 10 days, and you might not have revised this. So with that intention, I would like to review the Newton rational load flow. So let's share my screen. Let's begin by looking. By looking, I mean to say solving a simple two-bus problem. Now you can say already in lecture 15 or 16 we have already done this. So why repeating? Basically, as I said, Newton rational load flow is a next step for the next step of Newton rational load flow is FDLF. So that's why this will be useful, and it's also kind of a review as I was saying. So the two-bus system is something like this. So there is a bus 1 and then there is a bus 2, and then I'm just giving a very standard basic problem. There is a generation at bus 1 and there is a load at bus 2. Now the load at bus 2 is given as in per unit I'll mention. So 0.9 plus j 0.5. So this is the load at bus 2 in per unit. And then this line is having a reactance. So the reactance of the line, let's consider it as J 0.1 per unit. And then I have the V1 delta 1. So this is already known because for a two bus system, one of them should be slack bus. Since bus 2 is a load bus, automatically bus 1 will be designated as a slack bus. So let's say the voltage is 1 and the angle is 0 degrees. So very basic problem. This is also in per unit. Therefore, in the entire system, only thing that is unknown states are nothing but V2 delta 2. So these two things are unknown. What is the value of V2? What is the value of delta 2 are the two unknown values in this. So the question is, in the above system, so determine the unknown states. That is V2 and delta 2. So this is our basic question. And by now you should be able to solve it actually. You should be able to solve it in two different methods. The first method that we studied was Gauss-Seidel load flow. You should be able to apply Gauss-Seidel load flow and you should be able to solve this. So Gauss-Seidel load flow will have only one equation and just that one equation you have to iterate it and then out of the iterations you will get the final value of V2 and delta 2. And we have already done that in this course. Now, the other thing is now Newton-Raphson load flow. So let's do that. So you should also ask yourself, if I given this question in the exam, will you be able to solve it? And what are the steps, what is required, and so on. So far, before I continue, so far let me just get a confirmation. So you have any doubts regarding Newton-Raphson load flow? Because I am reviewing the topic. You have any doubts regarding that, or you have any doubts regarding the question that is there on the screen? So I'll just wait a couple of minutes to collect your doubts and then I'll start solving this. Go ahead and try to solve this problem. So what is the first step? So let's begin by forming Y bus. So Y bus is nothing but bus admittance matrix. So we have already seen several times how to do this. So just look at the two bus system. So there will be 2 by 2 matrix. So this will be a 2 by 2 matrix, 2 rows and 2 columns. So first, if you look at the off diagonal element, whatever is the impedance, so you write it as a Y12 is nothing but 1 by J0.1. So that will be minus J10. And once you get this Y12, you can just write it here. First row, second column. And of course, you will have to remove the minus sign as you already know. Same thing applies here. And then now coming to the diagonal element, there are no shunt impedances or shunt capacitors connecting bus 1 or bus 2. So I'll just add the rows and then give like this. So this is my Y bus. So this is just by observation. So what is step 2? In step 2, we write down the unknowns and equations. Corresponding equations. So what are the unknowns? So unknowns are nothing but V2 delta 2. And corresponding to V2, I'll write the equation of P2 and corresponding to delta 2, corresponding to delta 2, we'll write the equation of P2. Corresponding to V2, we'll write the equation of Q2. And P2, Q2 values are also known for you because that load is given. So what is the general equations? So again, we have derived these equations several times in the class. So these are very important. The generalized equations of what is the Pk and what is Qk. So this is the active power at bus K and this is the reactive power at bus K. We'll have a generalized equation. So I hope you can recollect this equation and this is very important. So let me write that. So I'm just pausing so that you can try yourself writing it. So it is I equal to 1 to n and then I have yki, vi, vk. These are all magnitudes. Then I'll have a cos function. Then I have theta ki plus delta I minus delta k. So this is the equation for pk, power at bus k. And the same equation with slight modification will be like this. We'll have a minus sign. Most of you might forget this minus sign, so it is important. So yki, vi, vk, everything is same except cos is replaced by sine. Now these two are generalized equations. So what is the specific equation for our case? So for our problem, specific equations for this problem. So what do we get? So I can just write P2 is equal to, so because it's only a one bus system, so I'll just get two terms. So I'll just write Y21, V1, V2 and then cos of theta 21 plus delta 1 minus delta 2. So this is one term and another term will be y22 v2 square cos of theta 22. So here delta 2 minus delta 2 will cancel out each other. So this is the first equation. So let me mark this as equation 1 or equation A. Now what is the other? Q2. So it will be exactly same just with a minus sign. So y21 v1 v2, the cos will become sine and then theta 21 plus delta 1 minus delta 2, again minus sign, so or I can just give overall minus sign, y22 v2 square sine of theta 22. So this let's call it as equation B. So I hope everybody is following up to here. So if you have any doubts or any questions, please feel free to stop me and you can always clarify your doubt and we can go forward. See, I'd like to go a little bit slow today because we are meeting after your midterm exam. So that's why. Okay, so once you have this, what is the next step? So the next step would be whatever values we have known, we can substitute them. Okay. So let's look at this. What is theta 21? So if you look at the Y bus, second row, first column, that is this one, and the theta will be 90 degrees, and so on. So by looking at that this thing, we can get some peculiar features for our equation. That is, one second. Yeah. So I have this now. So one thing you should notice that this cos of theta 22. So if you look here, theta 22 is this one. So minus j means minus 90 degrees, and cos of minus 90 degrees will be. Similarly, this sine will become, I think, minus 1. So we'll just substitute and try to solve it soon. So meanwhile, let's continue our thing. So without this, I have this equation A, and then I have the another equation B. So from these two equations, I'll just want to write it in the form of 0. So what you have to do? Simply take 0 equal to y21 v1 v2 cos of theta 21 plus delta 1 minus delta 2 minus p2. Just I bring the p2 on the other side. Similarly here 0 equal to y21 v1. Of course, I'll have a minus sign. Always we should not forget the minus sign. Then v2. This will be sine theta 21 plus delta 1 minus delta 2 plus. So I have this term. So this value will be equal to 1. So or equal to minus 1 actually, because this is minus 90. So but then this minus and this minus will cancel out each other, and this entire thing will become plus. So plus y22 v2 square. And finally q2 comes on this side, so it will become minus q2. So I have two functions now. So from this I can find to apply the Newton-Raphson method, I will have to find the Jacobian matrix. So what is the Jacobian matrix? So I have two functions. So first function and then first variable. So like this. So it is differentiation of my P2 function with respect to delta 2. Similarly, differentiation of my with the other variable, that is differentiation with respect to V2. Differentiation of Q2 function with respect to delta 2, and then differentiation of again Q2 function with, this is function Q2. So these two I'll just give the labels. This is function P2 and this is function Q2. And then this is with respect to V2. So let's differentiate this, then I can again write that. So you all have learned how to differentiate a function in your in your in your intermediate or in your BTech times. So just look at the first equation that is there on the screen. If you differentiate with respect to delta 2 here as it is shown, so the cos of delta, differentiation of cos is minus sign, but then because there is a minus here, that minus will get cancelled. So I get everything like this. So the first term will be this one. So this is the first term. That will be exactly same, y21 v1 v2 sine of theta 21 plus delta 1 minus delta 2. That's it. So this is the differentiation of the first element. So what happens next? Next we have differentiation of the first equation with V2. So very simple, here V2 is the variable here, just V2 can be kept, it's like everything else is a coefficient of V2, so V2 will be not there. I'll just write everything y21 v1 cos of theta 21 plus delta 1 minus delta 2 as it is. So this is my y21 element. Similarly, now look at the second equation and differentiate with delta 2. So again I get y21 v1 v2. Now the differentiation of sign is cos, but then because this minus sign is there, this minus sign will get cancelled. So I'll get cos of theta 21 plus delta 1 minus delta 2. So we have done this already. So this is what should come to you naturally. So I'm just revising it for you. Now again differentiate the second equation with respect. So V2 is a coefficient, and here also I have a V2. So we'll get two terms. So don't forget the second term. So let me write the first term, and then the second term will become plus 2 V2 Y22. Thus I have all the four uh, elements of the Jacobian matrix. Now how to do Newton-Raphson? So once this is done, so you can now use a step. By the way, I stopped counting steps. So this is step 2, and let's call this step 3. Formation of Jacobian matrix J. And once we have J now, so step 4 is nothing but your Newton-Raphson iterations. So what are the Newton-Raphson iterations? I'm sorry. So the Newton-Raphson iterations are delta 2 and V2 are the unknowns. So this is n plus 1 will be nothing but delta 2 and V2, which is n. So this is the values of the previous iteration, and this is the values of the new iteration. So this we want to update it. So how do we want to update it? It's nothing but you calculate the function value and then divide by Jacobian matrix. So basically invert the Jacobian matrix and multiply it here. So this is nothing but your Newton-Raphson method. Now for this entire thing, we had written one MATLAB code, and that MATLAB code, I think I'll just have to change the data to get the solution for today's problem. So let's try to find the solution. I mean, find that MATLAB code, and then we'll try to solve it again. So just give me a minute. I'll open the MATLAB code. Okay, so I have found the code. So let me just show you the MATLAB code for this. Again, this code is also available for everyone to download and try it yourself. So here it is. Okay, I think by now you might be able to start 16. I'm just revising it. If you have not tried it yourself, please, when you go home, open Octave or MATLAB and download this code from the link that I've given, and try to execute the code and try find yourself how it works. Let me just briefly review the code. So when you start, you begin at line number 1, of course, is clear all and TLC, and then the next one is just displaying the title for this code. Then you write 6, 7, 8, 9. Because it's a 2-bus system, I am defining the magnitude of the Y bus elements. And for today's problem, I think this is 10. So all elements magnitude is 10. Whereas the angle is pi by 2 for 1, 1 and pi by 2 for 1, minus pi by 2 for diagonal elements and pi by 2 for off diagonal elements. So up to line 6 to line 13 is about determining the Y bus. So that is done. So after that, when you go to defining the known states of the system, so what do I know? So V1 is 1 unit and delta 1 is 0, that is correct. Now P2 was the power demanded bus 2. So why the minus sign is there here is to signify that the definition of what is PK is total power injected into bus K. But then if there is a power demand, that means the power is coming out of the bus. So therefore, the P2 will be there. And for our problem that we have chosen today, I think it is 0.9 per unit. And Q2 is 0 minus 0.5 per unit. So that is correct. Then initializing the unknown variables that we know, that is delta 2 is 0 and V2 is 1. But then the final values, I am expecting V2 will be less than 1. Because reactive power demand is there at bus 2, the voltage cannot be at 1. It will fall as compared to V1. Similarly, the delta 2 will become negative because delta 1 angle is 0 and the power is reaching bus 2. So power goes from higher delta to lower delta. Therefore, if delta 1 is 0, then delta 2 should be negative and some value. So we will see how much value it is after solving it. So this x is a variable and d2, v2 are all just saved into x. Then I am running the iterations for 5 times. So that's why I am saying 1 to 5. And then I have two functions. So if you notice, this was our first equation, this is our second equation. Exactly the same equations I am writing down. So this is the calculated power and then scheduled power I am subtracting it. So therefore I positive or negative. So I have this FP2 and FQ2. Then just now I have written down J11, J12, J21, J22. So if you check your notes, these values will be similar, whatever we had written. So that values are all coming here. Y21 is V1, V2 sine of this. So T21 means theta 21. So if you refer to your notes that you have just now written and what you are seeing on the line number 30, 31, 32, 33, these are all same. Then finally I am making the J matrix by combining J11, J12, J21, J22. All these four I am combining to form a J matrix, which is 2 by 2 matrix. Then X is the unknowns, so therefore I just update the value of X. And then I am also updating the value of D2, V2 because these values are used in the equations above. And then I am displaying, and then the final value is also coming here. So I think everything is set. So let me just simply run this code and then see what happens. So I'll execute this code. And once the code is executed, you are able to see the solution. So So this the first number is the value of delta, and this the second number is the value of V. So V is 0.95, 0.94, and so on. Finally, in the end, the value of V is settling down to 0.94237. And the value of delta, of course, this is in radians. So when you convert to degrees, you will get minus 5.48 degrees. So this is the final answer. So I just executed our code, and then finally I got the answer here. So this one, I hope you all are able to recollect what we did in lecture 16. I'm just repeating in lecture 18. So let me write down the final solution. I think the name of the file, let me just check it. nrlf2bus.m. So this is the name of the file I have given, Newton Rational Load Flow 2bus.m. Output of this one. So is this. So finally, final V2 is equal to 0.94237 at an angle of minus 5.48 degrees. So this is as expected, the voltage is less and less than 1 per unit and the angle is negative. So this is about two bus system load flow. So now let me ask I'll just pause for a couple of minutes. So any doubts so far? So if you don't ask doubts, I will be asking doubts. So let me ask one doubt now and see if you can answer it. So if there's a question like this, what are the limitations of Newton Rational Load Flow? So you had seen the method, you had applied the method to a two-bus system, and if you had seen lecture 17, we have also applied to uh, three-bus system also. So after applying, after studying this method, after trying this, what do you feel are the limitations of this method in terms of finding the solution? So can anybody answer? So please use the chat window if you can answer this. Let's see. I'll give you 2 minutes time. Time per iteration is more. So these are all kind of, in a way, they are correct solutions. So let me just repeat them. So takes more time per iteration. Requires more memory. So these are the answers that are submitted by you. Time per iteration is more and all these things. Okay, so let's look at what is the reason. So for this, what is the reason? Why it takes more time per iteration? So can anybody answer that? Why it takes more time per iteration? And also the reason for the second one. Why it requires more money? Sorry, more memory. So sometimes what happens, this could be like a general solution that we follow, or you can just read it from a textbook or something. In the textbook it says time taken per iteration is more. Okay, therefore time taken per iteration is more. But then why exactly is it more? Why it takes more time? And also compared to what? More time iteration compared to what? Okay, so saying more number of equations. More number of equations is not the reason. So the time taken per iteration is more because, let me write, the matrix J has to be inverted inverted for every iteration. So when you are iterating the Newton-Raphson load flow, the matrix J has to be inverted for every iteration. So first of all, forming the matrix J itself is you need a lot of equations, and then you have to iterate, and you have to invert the matrix. So matrix inversion is a mathematical intensive method. Now requires more memory because there are more equations and variables. Of course, this second one is not that of a problem. So when the power system analysis started way back in 1950s, 60s and 70s, at that time the computer memory was important and was costly, and they have to conserve it. But now memory is not the problem, but still the problem is there with respect to the method itself, that it requires the Jacobian matrix to be calculated every iteration and then to be inverted, and inverting a matrix always a long process. So that is the doubt. So any other doubts you have? Well, I'll just got a quick call. I'll take. I have one question. Is there any condition that equations are implicit? So is there any condition? So this is JNTUKUCEV. So this is a doubt asked here. Is there any condition that equations are implicit? So first of all, did everyone understand the doubt? So what happens when the equations are implicit? So let me add that. What is meaning of implicit equations? So people also started giving answers for this. So less number of iterations, and then accurate and efficient. Okay. So there is another advantage here, that is fast convergence. So it's called quadratic convergence. So therefore no requirement for acceleration factor, as somebody has also mentioned. So that point also can hold here. So what is the meaning of quadratic convergence? Is that every iteration your accuracy will keep on increasing. That means if you are accurate up to one decimal place in one iteration, the next iteration your accuracy will be two decimal places, and the next iteration your accuracy will become four decimal places, and the next iteration your accuracy will become eight decimal places. So like that, very fast your accuracy will improve. That is about quadratic convergence. Is that number of iterations independent of size. So if even if there is a large system like a 10 bus system or 20 bus system or even 100 bus system, the number of iterations will still be less, but the problem will be in terms of time taken per each iteration will be excessively more. Question. So before answering this question, first of all, I was asking, does anybody know what is the meaning of implicit equations? Let me look at the solutions. Did somebody write something? What I would like to answer is, I would take an interpretation that J has to be inverted. What if J inverse does not exist? So in mathematics, every matrix may not have an inverse of it. So there are some matrix where the inverse does not exist. So what happens if J is that way? So that is the doubt. That's what is the thing that I understand by condition that equations are implicit. So, but then this problem does not occur in NR method, NR load flow method. So NR method it might occur, but NR load flow method. Again, this is best of my knowledge. If I make a mistake, let me know. So I'm always happy to correct it. Okay. So let's continue. Let's look at the disadvantages. So one of the disadvantages we listed out is it takes more time per iteration because J has to be inverted every iteration. So can something be done? So that something to be done is nothing but your FDLF, fast decoupled load flow. So this is so the objective to minimize or to reduce number of calculations. So by making some assumptions. So by making these assumptions, I can reduce some number of calculations. So what are the assumptions and all? We'll come back to that later. So just revisit our two bus problem, and we will write J matrix or J inverse matrix, whatever. So let's what I'll do is for each iteration. So what I'll do is I'll go back to my code and then I'll modify the code such that I take a print of J matrix. Then I'll see what happens with that J matrix. So let's do that as an exercise. So for this, let me share the screen. And then if I print this J matrix, for every iteration it will print. Let's see what happens. So now I'll execute this program. So now you can see this on your screen. The first value of J is, let me just run it once again because it did not print properly. Okay, so I have here, and let me disable this. So you see, on the screen you see this is 1 e to the power of 1. That means this is actually 10. E to the power of minus 16 practical is 0, and this one is 0, and then this is 10. So let me write these values back here. I got the values, so I'll just write this value. So the initial value of G, the first iteration, 10, 0, and then 0 and 10. So now you see, this is first iteration. This is J in second iteration. and this is J in third iteration. J in third iteration and then fourth iteration and so on. Now, can you compare what is the difference between these two? So you see, the diagonal element is always large. So this is diagonal element is very high value, 9.46, and this is 0. This is less than 1, almost like 10% of this. Similarly, in the next case also, 9.38 is very large value, and this one is a very small value compared to this. And this is very large value, and this is very small value compared to this. So, and from one iteration to the other iteration also, variation is not that much. See the first, so here you see the J matrix 0.46 becomes 0.38. Next iteration continues to become 0.38, and then next iteration also it becomes 0.38. And here you see the Jacobian matrix, this is 1515, then it becomes 0.6, then next also it becomes 0.6. So basically, so J elements, so after third iteration, the two decimals are fixed. After fourth iteration, you see the four decimals are fixed from here to here. In fact, the fifth decimal is also fixed. So 5 decimals are fixed. So very fast it is converging. And it's almost not changing at all. So why we should calculate J every iteration and find out. So that is the idea of the FDLF. Another thing, you notice how the J matrix is coming. So that is, what is the J matrix? So if you see the J matrix, delta 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 V, and the J matrix is there. This is delta P and delta Q. So in our case, this is P2 Q2 delta 2 V2 for our problem that we are studying. And notice that this J11, J12, J13, J14. So since the J11 is dominant and this is 21 and 22. Since the value of J11 and J22 is very high and the value of J12 and J21 are very low, so let's make an assumption. Assume J12 equal to 0 and J21 equal to 0. If you make this assumption, then the above equations will become decoupled. These assumptions will decouple the equations. Decouple P and Q equations. So what happens? So if I substitute 0 here and if I substitute 0 here, then I get two equations. Delta P2 equal to J11 into delta delta 2, and then delta Q2 equal to J22 into delta V2. So the V2 term does not come in the first equation and the delta 2 term does not come in the second equation. So therefore these are decoupled. So why we are assuming this as 0? So just by our, of course I will also give the practical or the theoretical justification for that. But if you look at our Jacobian matrix, all the time this term is anyway 0. I mean this term is relatively very small compared to this one is 8.89 but this one is 0.9. So hardly 10% of that. So this is a common practice for in general in every case. So for a regular power system, these elements are all anyway small. So by doing this assumption, we can make the code faster. Another thing that you can notice is, if I give you, so it is easier to invert a matrix. Invert a diagonal matrix. I don't know whether you had studied this before or not. So let's say I give you a matrix A equal to 5 0 0 2, not 2. Let me say, let me take 4. Find A inverse. So this is a diagonal matrix. So I'll also give another matrix B equal to 6 0, not 6. So let's say this element is 20, 20 minus 10. So, so this is a diagonal matrix. So A and B are diagonal. So how do you find the inverse of a diagonal matrix? Can someone find A inverse? Invert individual elements and it becomes your inverse matrix. So for example, A inverse will be nothing but 1 by 5, 0, 0, 1 by 4. Similarly, B inverse will be nothing but, so let me write it here. So B inverse is nothing but 1 by 2, 0, 0, 0, 0, 0, 0, 1 by 20, 0, 0, 0, 0, 1 by minus 10, 0, 0, and 1 by minus 100. So you can just verify. In fact, if you multiply B into B inverse, so 2 into 1 by 2 will be 1, and then all other terms will be 0, and then 20 into 1 by 20 will be again 1, and so on. So you get an identity matrix just by multiplying these two. So from that itself you can tell. It's very easy to invert a matrix. Now if you go up, what you notice here, by making this assumption that the these elements are 0, J12 and J21 are 0, I can decouple the equations and I can easily find the inverse also, and then I can solve the problem very fast. So from this assumption, so can you once again quickly solve the above problem? So just this is our assumption, everything else is same. Using this assumption, can we solve the problem faster? Is what is our doubt. The J equal to J11, J12, J21, J22 by assuming J12 equal to 0 and J21 equal to 0, the problem becomes simpler. Now, in fact, if you look at the initial J, in the first iteration, what is our J? So we got actually 10, 0, 0, 10. So if I just go by this, let me just quickly refer what we got in the first iteration. Yeah, so 10, 0, 0, 10. So if I just go by this, then it will be even better. So I have an idea now. The idea is like this. So can we solve two bus system with this assumption? So let's try that. So what we have to do is delta P delta Q is equal to your J matrix into delta and delta V. Or if I write it as a NR method, so what I'll get is the value of delta and V, delta 2 and V2 in n plus 1th iteration is nothing but whatever is the old value of delta 2 and V2 in the nth iteration. This one minus Jacobian inverse multiplied by function P2 and function Q2. This is what we did last time. Now what is the change we are doing is this initial value anyway we are taking same. This is fixed now. So J is fixed and decoupled also. And then FP2, FQ2 only I have to solve. So let's modify our NR code. So when I say modify, I want to simplify and see if we get the same result. Solution for V2 and delta 2. So this is the experiment we try to do now. And strangely enough, I have not done it myself before. So this is also something new for me. So let's try it. So now I'll go over to the code and then we'll do some modifications to the code. And once we do this, we'll compare the solutions. So on your screen, you have the same code that we just saw sometime before. Now I'll just make some changes. So up to here everything is same. Just calculation of Jacobian element I don't require to do. So once I define the Jacobian matrix outside the for loop, I just come into this one, I just simply delete all this. And then I'm doing this. Inverse of Jacobian into this. In fact, this inverse also I don't have to do. I can do individual elements inverse. And then now you see I deleted a lot of programming code from the line. So therefore, in the textbook you might have seen it takes less number of iterations. So this is what is the meaning that it takes less number of, it takes less calculations per iteration. So because I have simply deleted a lot of equations that were there. So now will this work or not is the interesting thing. Now we are doing 5 iterations, so let's do 5. And if you remember for Newton Raphson, I think 2 or 3 iterations we got the solution. So but then let's see how many iterations this will take to converge to a solution. So I hope and I believe we have everything to do this. So let's run this code and see. So only change I made is simply I defined the J as a constant matrix and deleted the equations for J. That's all. Everything else is same, Newton Raphson only. So some values are coming, but then if you notice, the solution is not converged. So after 5 iterations, the last 2 decimal places still there is a change. Here 942414 is there, 942337. So up to 3rd decimal it is matching, 4th decimal not matching. So let's increase the number of iterations. Instead of 5 iterations, let's do 10 iterations. So now let's see. Okay, so looks like after about 7 or 8 iterations, my solution is converging. So the last solution is this one, 956 and all these things. So I hope you are able to see that on the screen that in the last iteration we are getting the solution. So in fact, this is not, let me change the title also. This is simplified. So there you can see the title, simplified Newton-Raphson two-bus system. And the final value is this. And I think this exactly matches with our earlier solution. The V2 is same. Only difference is now this time I require more number of iterations and then more number of iterations, but faster it is. Less number of calculations per iteration. So let me write down the solution here. Inside the J and J inverse. Two things, J also we are not calculating, J inverse also not calculating inside the for loop. And we found solution after 10 iterations. And this is our solution. So this is V2 and this is delta 2 degrees. So 0.94237 at an angle of minus 5.48. I think this is the exact solution we got earlier also, and it is matching. So I hope by this simple with this simple idea, or let me write it, this is the idea behind FDLF, fast decoupled load flow. So the idea is let it take more iterations, but it will converge fast. It will converge because it will take less calculation because J and J inverse are not calculated in every iteration. So any doubts regarding this? So far what you have seen, any doubts on that? But then now since we have only about 10 minutes left, I don't want to go into the details of FDLF also. So that's why I'm pausing for your doubts. Behind FDLF. So next class we'll see about FDLF in more detail. So fast decoupled load flow in more detail. I think there will be some derivation also. So, but before you come to the next class, I'll try to give you some homework. So the homework is like this. Look at online lecture videos of lecture 17, 18. I'm sorry, today's is 17, right? So 16 and 17. So this is the first homework. Second homework is practice the 3-bus problem of NR method. And the third one is, okay, so when I say practice, you can do both ways. So one is hand or calculator, and our calculator calculations. And you can also do using MATLAB code. So code is also available, that is there in the home page. You can download the code and then open the code in your computer. You can run it and then check. And the third one you see is try to write code for simplified NR load flow for 3-bus system. So today in the class we did for 2-bus system. Try to do it for 3-bus system and then check if it really converges or not. So if there are no doubts, I'd like to finish a little bit early today at 12:20. So, but then I'll wait for a couple of minutes if you have any final doubts. Okay, so if there are no doubts, then let me conclude today's class. So today we had just revised, this is the first class after your midsem exam. So we had briefly revised international load flow, and then I have given you a basic idea of FDLF. And next class we'll actually implement FDLF and then see what happens. So with that, let's conclude. We'll meet in the next class on Thursday. Bye.